Hello everyone, and thank you for attending today's webinar, How to Use NPAR in OIM Analysis version 8. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions, you can click on the Q&A widget and submit them. We'll try to answer these during the webcast, but if a fuller answer is needed or we run out of time, you'll receive an answer later via email. We do capture and answer all questions. A copy of today's slide deck and some links to additional materials are available in the resource list widget that looks like a green folder. You can expand your slide area by clicking on the maximize icon on the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulties, please click on a help widget. It has a question mark icon and covers common technical issues. Finally, an on-demand version of the webcast will be available later today, and it can be accessed using the same audience link that was sent to you earlier. Now I'd like to introduce Sean Wallace, who's our presenter for today's webinar. Sean joined EDAX in 2015 as an application engineer specializing in EBSD. He has a strong background in all sorts of instrumentations, including EBSD, electron microprobe, all sorts of mass spectrometry, and computed tomography. In his career, he has taught researchers of all levels, from postdocs to undergrads, how to use instrumentation, and he continues that here at EDAX. Sean earned his MS in geology from the University of South Carolina. After earning his degree, Sean worked as a scientific assistant at the American Museum of Natural History in New York City, where he helped study the origin of the solar system using EBSD and other instruments, including 3D work with computed tomography. When Sean's not busy running samples, he can often be found in nature, either hiking or fishing or just staring at rocks. So now over to you, Sean.
Hello, everybody. It's nice to be here with you guys to share with you how to use NPAR in OIM analysis. It's kind of changed a lot of things of my workflow, and I wanted to kind of make sure that you guys understood, how to use it, how we use it in-house, to better explain, again, the functions inside of it and how they go with your workflow. Again, because like NPAR has literally changed everything I do, from data collection to data processing. So I think it's very, very important for you guys as our users to understand how we use it and to go from there. So to start off with, we'll talk a little bit about the basics of EBSD mapping. So for EBSD mapping, we're basically just collecting patterns on a regular sampling grid. Nothing too fancy, just point to point to point. So you have X and Y coordinates with a pattern. We default to what's called a hexagonal grid. We do this for two main reasons. One, it has a better density of points, and two, you have 6 equidistant neighbors. That 6 equidistant neighbors is very important when you're doing kinds of maps, because then every data point, the center, is always the same distance between those centers. If you do a square grid, you don't get that. Because of that, your data can actually be biased because of that. In a sense, we do this grid. This hex grid is kind of important for NPAR, and I'll go ahead and talk about that. And here's why it's important for NPAR. So NPAR stands for Neighbor Pattern Averaging and Reindexing. It is our new approach. It's a patented approach to basically improving the signal-to-noise ratio while maintaining the same acquisition speeds. Previously, if you had a sample that was either a poor diffractor, you just couldn't get good patterns off of it, you would do frame averaging. So you take 2 or 3 or 5 patterns from the same point, average them together, and then move on. While doing this would also increase your collection time. And if I take the double amount of the patterns, I just double my collection times. Now, we all know with EBSD maps, you can have a very long map, and doubling a very long time makes it even longer time. So this method uses a slightly different approach, saying, okay, I'm going to take those 6 nearest neighbors. I am going to push the pattern basically to the middle. I am going to average all 7 of those points, and then I'm going to reindex it. And this is a very, very important thing to not gloss over, is the fact that we are fully reindexing the pattern. So I have the pattern in the middle. It's an average of all 7 now. I'm starting back over and redoing from the Huff level all the way up, including the background. And we're going to talk a lot about the background in this because a lot of the options that exist in OIM Analysis 8 for reindexing have different backgrounds. And these backgrounds are just as important when you're dealing with these data sets as NPAR itself. And we're going to see the power of those backgrounds and really just kind of how they start to pull out that data that really kind of helps you, again, push the limits of what we can do with NPAR. And I've had multiple times already in the last year with NPAR where I've had samples that I wouldn't even think about doing, and was able to get good, consistent data on these samples, again, that would just sat there and say, hey, sorry, we can't do these. That's not what we want as a company. We want everything to be doable, but at the same time, NPAR expands that group. So essentially, with this approach, again, it allows me to increase my frame rate and basically, again, collect data at better speeds on more difficult samples. I can also collect faster at lower beam currents and accelerating voltages, allowing for better spatial resolution, and also is better for beam-sensitive samples. And the other thing it really helps you do is get more data out of the data you're already collecting. So, you're able to get a little bit more information from the data sets you already have. We've been finding customers have been going back over data sets they've had for, 2 years, as they say, with patterns, to essentially pull more and more information out of them. Again, NPAR I've been finding very useful for things like ceramics. It seems counterintuitive, but with non-conductive samples, where charting becomes an issue, I've actually found the faster I go, the better the data I have. Again, it sounds kind of counterintuitive because, hey, I'm actually getting less signal, but I'm actually dealing with less charging effects. So because I have less charging effects, I'm getting more signal, even though I'm going faster because of NPAR. So again, it changes everything I'm doing with my data collection process. That again, in the past, I'd just say, okay, I need to go slower so I get more signal. I had to do frame averaging. And again, all these kind of slow down my data collection process. So with NPAR, that's me, okay, I'll collect my data, rerun it later on, and go ahead and do that. Again, it's something I should mention now is that NPAR is a reprocessing step. It is not currently done live. We only do it after the data has already been collected. So with that, I'll just kind of show you some quick results we've seen with NPAR. This is a pretty common kind of thing where you see a relatively noisy data set like this, where you have, an 11% indexing success rate. You go ahead and run it through NPAR, and it gets it up to the high 90s. I've seen actually worse data sets than this that are proprietary that have gone from like 3% to 99. That was a ceramic sample. It is, again, it's just about finding those samples that you have that are traditionally hard for EBSD, and NPAR really just kind of gives them that extra leg up to make that data set go from, a little noisy, but maybe slightly usable to honestly often not pristine data sets. And that there is really the true power of NPAR. And here again, we can just kind of see how the pattern quality can really kind of be extremely poor and still give you good indexing results. So here is a little bit of a graphic here. In the first column, you can see A, B, C, and D. Those are the patterns. So those are the patterns before NPAR. And then you have the traditional EBSD indexing approach versus the NPAR indexing approach. And you can see between the traditional and the NPAR, as you get worse pattern quality, you're actually not getting any differences in your end results. So with NPAR, you're again able to take those noisy data sets and actually pull that data out and get good quality data on the entire data sets using NPAR. We have started to and have dove pretty deep into understanding the performance of this and the effects it has on your data. I'm going to touch a little bit on that in the end, but I highly suggest all you hopefully can see our presentations at M&M, where we kind of go in depth on a lot of this stuff on the scientific side, looking at what is changing, how is it changing, and when in the end, what does this affect on your data? And in the end, that's all really, really kind of an interesting thing to understand. Okay, what's going on with my IQ map? What's going on with my CAM map and different things like that. So again, it's a powerful tool to have at your in your tool set, and that's really what NPAR is. It's a tool. So one of the big differences here is again that's specific to OIM Analysis 8 is that in previous versions of OIM Analysis, you're allowed to basically analyze the data of already indexed data sets. You could not reindex a data set inside OIM Analysis. You'd have to go to OIMDC or team, reindex the data, bring in the new file. With OIM Analysis 8, we've actually allowed full reindexing of data sets inside of OIM Analysis. So as long as I have saved patterns, I'm able to essentially go ahead and redo that data however I want. And that's what we're going to cover kind of detail in this. So again, I'm able to pull that data in, fully rework it, reindex it, look at the patterns and all this stuff inside of OIM Analysis. And the other reasons of questions of like why to reindex inside of OIM Analysis is because essentially there's options inside of OIM Analysis that do not really exist in Team. And for technical reasons, often you really can't. A couple of those things are going to be partition-based backgrounds and reindexing. So one of the main features of OIM Analysis is that I can go ahead and start pulling things apart. I can say, okay, here I just want to pull out these index points with our CIs are low and just reindex these. I can't do that in Team. I can also do partition-based backgrounds. I can say, okay, the background for this phase is not that great. I can go ahead and basically pull that out, redo my background, and then reindex just those points. Other things I can do is easy recalibrations of older data sets. So we have a tune function basically inside of OIM Analysis 8. I can pull in that data set, recalibrate it, and then rerun it, the full indexing based on that. Auto brightness contrast on each pattern. So I can basically stretch each pattern and give me a little bit better contrast and easier for the HUF to do it. I can do manual point reindexing, which means I can essentially say, okay, I have this one data point right here that's not great. Let me just go ahead and reindex that data point. It works for data sets where you have 2 or 3 or a very small area. Again, you can do it by hand. But of course, you can reindex entire data sets also. The other thing is I have batch reindexing and batch chi-scan. So if I have a large 3D data set and I want to reindex the entire thing, it's essentially just one extra button push. I say, okay, everything I did to this data set, do on all of these data sets, and it just runs and runs and runs. You're doing 50 data sets, it might take a while. You push the button, go out to lunch, come back, and the data's done. And the same thing with chi-scan, or chemistry-assisted indexing. Since we have the EDS data essentially with us, when we come over to OIM Analysis, I can use the chemistry-assisted indexing along with NPAR to run both at the same time. So I'm starting to able to basically, do partition-based. I can do batch processing, recalibrations. There's just a whole bunch more of these tools that are at my disposal now that I'm doing some of my indexing, reindexing offline instead of doing it inside of Team. And with that, I kind of got a question for you guys. One of those questions that's useful to understand exactly my audiences. And I want to know what version of OIM Analysis do you currently use? OIM 8 is still relatively new. And because of that, it's always good to essentially, see how many of you are using it, how many are using OIM Analysis 7 still, or maybe even older, because I know there's customers out there using 4 and 5, while, of course, right now we're at 8. And of course, some of you may just use open source solutions like MTEX, which are perfectly reasonable, but we don't have much control over what goes inside of it. So I just kind of want to know, what are you guys using? To better understand, essentially, again, what you guys are using and how your workflow is currently going in those. So go ahead and give this a minute to see how it works. So it's going to be interesting to see how this turns out. Oh, okay. So here's our current breakdown. Our current breakdown is about 25% of you are currently using OIM Analysis 8. It's actually higher than I would expect it to be since OIM 8 has not been out that long. About 50% are currently using OIM Analysis 7, 20% using older, and about 10% using open source. So I mean that's about what I expected, except for the OIM 8-7 split. I expected that to be a little bit higher. So it's good to see that OIM 8 is getting out there and that you guys are using it. Again, it's not there's not many changes to OIM Analysis 8 and 7, but the big one, of course, is going to be this indexing, and that's why we're covering it. So with that in mind, I'm going to go ahead and start diving in, basically, how to do this. And the first thing I want to stop by and say is that inside OIM Analysis, we took our time, and we have fully rebuilt, updated, and expanded the tutorials that exist inside of there. There's currently, I think, 10 or 11 tutorials built on the sampled data sets inside of this. I'm going to be using the high gain nickel for most of this work, just kind of so that you guys can come back here, basically watch the webinar. And if you want to, you can follow along and say, okay, here's what he's doing. And this is, the data set is the same data set, so you can see the results in the end. Again, we know that OIM Analysis is a tool that is essentially, I like to tell people, grows with them. It can do from the incredibly easy, from basic IPF maps and IQ maps and things like that, to the incredibly complex, where I'm looking at Taylor factors and Schmidt factors to understand relatively high-level understanding of slip systems and how my materials would behave if I start actually, doing, stressing it and things like that. So again, we understand that it goes from the easy to the complex, and we hope to be able to guide you basically as your knowledge grows. And that's the point of these tutorials, is saying, okay, hey, here's this data set. Again, there's a whole bunch of sample data sets included with OIM Analysis 8. And because of that, we want you to work through those to better understand what you can do to the data and the workflow for that. That's often the most questions I get is, how do I do something? And usually the question isn't if you can do something in OIM Analysis, it's how to do it. Because if you've thought about it, it's probably already in OIM Analysis, because OIM Analysis is basically our workhorse and has been now for 20 years. So at that point, it's just an incredibly strong tool for any sort of analysis you want to do. So what do I need to index? And this is kind of very, very important, because we need to have the data to work with. So to reindex a data set inside OIM Analysis requires an OSC file and the pattern files themselves. To save the patterns in Team, you go to the EBSD Mapping panel. It's in the advanced options, and just basically click on Save Patterns. There's a couple different file formats to save the patterns in. There's going to be the .pat file, the UP1, and the UP2. We suggest the UP2 as the best one. It's just basically for technical reasons. The .pat file tends to be a little bit larger, is my understanding, but the UP2 one is kind of tends to be the best package for the pattern files. One of the other things to keep in mind when dealing with these data sets is that currently, anytime Team is closed, we turn the save patterns off. And the reason we do this is because these pattern files can get very, very large very, very quickly. So if we defaulted it to on and you weren't really paying attention to what was going on, your hard drive could be full in a week and a half. And we don't want you to go, okay, here's my data, and suddenly my computer's full. Why? And we want it to be a conscious decision for you to say, okay, I am saving the patterns. I think in the future we're thinking about changing that so that it can be a user level toggle. But as of right now, again, it always defaults to off when any time Team is closed. So again, keep that in mind. We have to have the patterns to reindex, because again, we're going all the way back, redoing the HUF, and then going through our indexing routine. So I need the patterns. Without the patterns, I can't reindex. So with that, we have a sample data set. Here you can see we have it. Here's the project, the file path. You can see is default, and you can see there is quite a few sample data sets inside of this. Again, I'm going to be using the high gain nickel data set. It is essentially just a nickel sample that we ran at very fast speeds and very high noise levels. And with that, we're able to, in this case, basically degrade a data set on purpose to start to show the power. Again, the data set itself doesn't really matter. I mean, in this case, the data set we made bad on purpose, but often it's, you can do on samples that are bad because it's just a difficult sample to get a good pattern off of. And I think we all have dealt with those recently. You get those samples and everything's not a perfect metal sample, and that's what keeps my job fun is, I got a couple samples on my desk right now from a recent customer that, it's going to be not particularly easy, but at the same time, I know NPAR is going to be there to essentially help me and say, okay, here's our tool. got a question here about about using OIM data collection instead. Yeah, it doesn't really matter if you use OIM data collection or team for doing NPAR. The only difference is basically where you have to collect and save patterns. Again, as long as I have the OSC data set and the pattern file, that's all I need. And that's the key. They both are able to save patterns, so we're able to do NPAR either in OIMDC or in team. So that sample data set I showed you guys is relatively, again, straightforward. The first step is always going to be to load the patterns. By default, we do not load the patterns because, again, the pattern files can be relatively large themselves. And because of that, we don't want to, essentially, we don't want to load down the computer by, you open up 5 data sets, you open up 5 pattern files, and suddenly using 40 gigs of memory. You don't want to do that. So we make it a conscious decision, again, to load the pattern files. And the way to do that is you can see the little square there, this little circle, excuse me, with the Kikuchi ball, basically, the fraction pattern there. That is the NPAR way to open up a data set. So I have any sort of map open. I click on that icon, and then I click on the data set itself, and it'll initialize the patterns. So again, this basically starts to open up the pattern files, put them into memory, so that I have access to them. Again, this is a non-trivial step because, again, usually because of the data size. These data sets can be quite large. So after that is done, the thing I usually do is to, 1, make sure the pattern's loaded correctly, and 2, just kind of reorient myself and say, okay, what do these patterns look like? And so when I do that is I click on what's called Flexi View on the right side of my map. The Flexi View panel is useful because it essentially gives me more information about my map. There's a couple different methods there. There's like the unit cell flyby, which uses the orientations to put up a crystal unit cell. There's also going to be the reconstructed HUF. So it has HUF data. It can basically reconstruct a pattern by that. What we're going to be using is the EBSD pattern flyby. And go ahead and basically click on Add, click on EBSD pattern flyby, and add the window to there. And what I'm able to do now is basically look at the patterns. And when I do that and look at the patterns, they essentially they just pop up as I mouse over this. That's going to be one of the main differences between the flybys versus the statics. The flybys essentially follow my mouse. So as I mouse over the area, I am able to see the patterns in that area. And the reason for doing this, again, is to kind of look at it to understand the quality of these patterns, if there's any spatial variations in these patterns, if there's any phase differences. If I can see phases, sometimes they act completely differently if I have different diffraction strengths, just to kind of, again, start to understand my data better and make sure everything is kosher. And with that, it's really getting kind of understanding what we're doing. The other thing to realize is that this is a raw pattern. You can see that there's noise on the outside. You can see the pattern's pretty darn weak. You can see, basically evidence of one zone axis and maybe a couple others on the side. So what we really have to do after this is construct a background. And the reason we need to construct a background is twofold. Give me a second here. There we go. Okay, push the slide. So here, the reason these backgrounds are important is because they do a couple of different things. 1, they remove the intensity gradient. So anytime I have a background or take an EBSD pattern, the pattern center is going to be the first area that's hit. And because of that, I have basically a hot spot, and the gradient comes out from there. So the background removes that gradient, and it improves band contrast. And in the end, our goal is always to help basically for the HUF to find the lines. And if I have the better band contrast, it makes an easier job for the HUF to do so. I don't have any rogue bands then. I have good well-defined bands. My precision increases. So again, basically, my goal here is always basically to help the HUF do its job. And the background is going to be the most important part. So just kind of get a step through of the background process. So go ahead and step back real quick. This right here is the pattern view, the point information that I have when I am basically doing NPAR, where I'm in the reindexing routines inside of OIM Analysis. In the middle here, you can see the big screen. That is the pattern view. And on the left are our different options. Top is going to be reindexing. Next button there with the little circle thing is going to be undoing the reindexing for that point. And the other ones are just different options of toggling off the HUF, toggling on the indexing solution or manual band detection. Down the bottom left, there's going to be the things, basically the buttons to say, okay, reindex this point, reindex the data set, reindex the entire batch processing, and the same thing with chi-scan underneath there. So again, there's a whole bunch of different methods, but again, these should look relatively familiar to you because they're essentially the same tools that already exist in Team and the same tools that exist pretty much anywhere else. On the right-hand side is going to be essentially our options. The pull-down menu can also be controlled by the F keys, the function keys, so F1 through 9, I believe, are able to switch through them relatively quickly. The main one for today is, of course, going to be our background, and that's controlled by our image processing tab. So here we can see both the NPAR on top, we can see the data set background subtraction, we can see the partition, the dynamic, and then of course the auto brightness contrast, and in the end it's going to be the advanced. With all of these options, each one has got a little bit different power to it, and with that power you will start to kind of, again, start breaking these down to see exactly what they do. So here's this raw pattern, kind of keep that in your mind how it's not a very good pattern, and if I just turn on NPAR, I'm able again to start to see the quality of the patterns in NPAR. So now all I've done is basically turned on NPAR. So now I have those 7 patterns averaged together, and I can see, again, way better band contrast versus the previous one. I'm just going to toggle back real quick. So here is the previous image. You can see evidence of some lines, switching lines, but in the end, NPAR turns that pattern into this. So there we've gone into basically this is an indexable pattern already, but we can go one step further. So in this case here, I can, let's say, look at just the dataset background correction. So the other option here is going to be the dataset background correction. This essentially takes 500 random points and uses that to make a background. So here again, you can kind of see with the dataset background correction on, it helps to better define it. The other one is going to be the partition-based. So if I have my data already partitioned, I can just do a partition-based background, and that essentially just takes up to 500 patterns from that active partition. Often, and this is the case in this data set, if I don't have any partitions, the data set background and the partition-based background are actually the same. So again, if the database is not partitioned, the data set will essentially be very, very, very similar. Again, it's 500 random points, so you shouldn't usually have any sort of big changes to it. But you know, there's always randomness because we are picking random points in the data set or the partition. So again, we can see here that we start building up different kinds of backgrounds. The other background I often find useful is going to be the dynamic background. The dynamic background basically smears out the pattern itself and uses that as its own background. This background is best used on multi-phase samples with different diffraction strengths and also on rough surfaces where the gradient of the pattern is much more non-uniform. And again, you can see the differences here with the dynamic background. You tend to get a little bit less contrast. And the other option, the main option that most people are going to use is going to be the auto brightness contrast. Essentially just does a quick stretch and gives you better contrast on the pattern itself. And with that, you can really kind of start to see that, again, all these options can be used in conjunction with each other to kind of make these patterns have better and better contrast, and in the end, to get better and better results. So again, we have things like dynamic background for multi-phase materials, static backgrounds, and partition-based backgrounds for those kind of materials, and then go all the way to auto brightness contrast depending on what's going on. So all these different steps essentially just kind of help you do that. There's also the advanced options where you can essentially look and see what it's doing to the histogram. And again, there's a whole bunch of different options in there. And most of these options, again, you're going to be familiar with. They're all the same things that exist from OIMDC and also from Team. It's just a kind of a different wrapper. So you can start doing your different pass filters, of course, your static backgrounds and all that kind of stuff that you're used to. And here again, I can also start saving and loading different kinds of routines. So if I do the same thing over and over again, I can save that as a background routine and just load it here. So again, it's just different ways of looking at your data and starting, again, our ultimate goal in the end is to get nice, clear patterns, nice, clear lines so that the HUF can do its job. And with that said, you usually don't use just one of these options. I could just use one of these options. I could just use NPAR for every data set, or I could use, you know, just a dynamic background. But what I usually do for most of my work is going to be multiple of these at the same time. Anytime I'm doing NPAR, I usually use NPAR with a dataset background subtraction. And you can see here in this case from this nickel sample, I'm getting a nice clear pattern, easy to index. This is going to be my standard background for probably about 90% of my work. With NPAR and the dataset background correction, it really just makes the things start to pop. And with that contrast, it's easy to actually go ahead and get the good quality data that we need. Again, that's going to be my standard background for, again, probably 90% of my work. If I am dealing with more of like a geological material, and here's, sorry, it goes by step by step. So here you can see the difference between these. So this right here is just the raw pattern on the left. And the one in the middle there is just with NPAR. So again, you can see NPAR starts to show you those lines better and better, but I really need to add NPAR with the dataset background correction to get a good indexable pattern out of it. So again, not only do I just start off with raw patterns, I usually use NPAR and the dataset background correction at the same time to really, again, pop those lines that I'm able to go ahead and get that. And with that, again, it's my standard formula is NPAR and the dataset background. When I'm using usually multi-phase materials, I will often also add the dynamic background. And the reason for that is pretty simple. It's what the dynamic background has and what it does. Works really well in multi-phase samples. So in this case here, you can see I have NPAR selected on the right side. I also have the dataset background correction selected. But in this case, I've also added the dynamic background. And again, that helps me basically even out my background on multi-phase materials. Because when I'm collecting this data and I look at it, let's say I have, again, let's say a geological material where I have either like a metal phase and some sort of like feldspar phase, the diffraction strength between these two is very, very different. Because of that, if I do a non-dynamic background, I can actually either oversaturate the material, the high diffractor, or undersaturate the lower. The use of the dynamic background allows me to essentially find the good kind of middle ground to help me pull that out. The other way I can do this is I could start to partition it. And if I did the partition-based way, I could, instead of using a data set background, I could use the partition-based one. And because of this partition-based method, I can say, okay, just do like this EDS data, break it up into just heavy iron stuff, the higher diffractor. I can start basically rebuilding it by phases and say, okay, this phase, this chemistry use this use this, and I can start breaking it down into different basic phases, different partitions with different backgrounds. But again, I usually find the dynamic background does a relatively good job, and I use both the dataset background correction and the dynamic background. And the reason I do that, again, is because the dataset background corrects for basically my normal camera operations. So like things like my gradient. So my gradient is gone usually with the dataset background correction. But if I have different diffraction strengths, that's when the dynamic one becomes in handy. So it's a combination of both these that really kind of helps with the geological samples to start pulling it apart. So again, that's my background, my standard formulas for those two. The next step is always to consider in these is going to be the recalibration inside of OIM analysis. This is not something you always have to do with your data sets. I find it very useful for me because I'm often not dealing with my own data sets, and there are systems out in the field who've been used by different users. So essentially, the initial calibration is part of the OSC file, and we read that in, and we know where we are basically in geometry. The next thing though is that I can always kind of better tune it to slightly get better results. It's also again very, very useful when dealing with data sets from other systems, just kind of to cross-check what's going on. With that, we can talk about how to do the recalibration. Now, that nickel data set I showed you previously is probably a data set I would not recalibrate on. And the reason I would not recalibrate on it is because when I'm doing a calibration, I want to try to get the best pattern I can. And essentially, the quality of that pattern controls controls basically how precise my calibration is going to be. So my step one is basically to use that EBSD pattern flyby to find a good pattern. And the way I usually do that is I use the IQ map. So the IQ map is basically understanding our band contrast. Often it has orientation effects in it. So if I can find a bright spot on my IQ map, I usually have that's where my best patterns are. So I go to the IQ map, open up EBSD pattern flyby option, look for it, select it, and then click on it, and it's going to open up the next window. The other thing to keep in mind here is that you usually want to keep the area you calibrate on towards the middle, because there can be a slight shift in your calibration from the top to the bottom of your scan. This becomes more of an issue at low magnifications because that difference between the top and the bottom of the scan can be quite large. If I'm working at higher mags, the difference can be relatively small, and because of that, it's not as important to really nail it. But again, if I'm doing low magnification scans and I'm recalibrating it, I want to usually aim for the middle itself. So with that in mind, it's essentially you just, again, be careful of recalibrating with marginal patterns because, you just can't really find that. You want it to be precise. And with something like this nickel where it's very, very noisy, there's a little bit of wiggle room and that will affect the entire reindexing. Everything's usually going to be off by a little bit of a systematic error, but because of that, again, it depends what in the end, what's the purpose of my data? And, if it's to get a good coherent data set with high precision, then again, you have to kind of think about, should I recalibrate or should I trust my old calibration? So again, something to kind of keep in mind. So when I have that over there, I basically click on it and it brings it up into the map. And I go ahead and change the right side pull down menu to the calibration. And here I can see a couple of different things. I can see the phase listed. I can see the current calibration, X star, Y star, Z star. And then I have my tune button and a couple other different options down here. Again, the X star, Y star, Z star is essentially just telling me where I am in space. The most important one tends to be the Z star. And the Z star is going to be essentially the distance between my sample and my phosphorus screen. This is essentially our scaling factor to understand, when my pattern is formed, it radiates out as a sphere. That sphere hits an object and hits our phosphorus screen. That distance changes with our scaling. So as I'm closer to my phosphorus screen, I see more. As I'm further out, I see less. And we need to be able to understand this value so we know basically what area I should be looking at in the Kikuchi sphere and in the fraction sphere to understand, again, that scaling factor of how I should, basically look at my data. With that scaling factor, if it's way off, you'll see it. Everything looks like either squished or blown up too much. And again, that's why the Z star tends to be the most important one. So usually when you tune a data set, you click on this tune button, what happens is the Z star is going to change and the X and Y star is going to change usually a relatively small amount. And with that is basically you're looking at, okay, I just redid the calibration based on that pattern. On the bottom here, you can see what has the original and the fits. And those are going to basically tell you how good the recalibration was or how good the old calibration was too. In this case here, you can see a relatively small change in the fit. So that wasn't making any sort of big changes in the calibration. And with that, again, it's just kind of saying, okay, they probably need to do it with this data set, but it never hurts. So the other thing to make sure you're doing it with is you got to make sure you check the phase. If you have a multi-phase material, the pull-down menu, you're basically telling it which phase to use. So just basically just make sure you have the right one. And after you do all that, just click on Tune, double check the values, make sure they make sense, and you're done. It's really quick. Again, it's pretty much a 2 or 3 step process, and with that, you're ready to go. So now you got essentially loaded up the patterns at this point. We fiddle around with our backgrounds quite a bit, and now we've moved on to recalibrating. The other thing again to keep in mind is what we call the PC center shift calibration. It's important to do mainly on low mag scans because the pattern center shift will be much larger. And again, it's correct for the working distance changes from the top to the bottom of the sample. If you're doing low mag, you don't really have to do this. You don't even really have to. Again, if you don't do this, it can mess with a couple different. It can add systematic error to your data sets. So here you can see the PC SIFT calibration down here at the bottom, the auto models and the manual ones. The auto models basically just randomly find patterns and does it for you, while the other manual one, basically you find the points and then it calculates it off those points. I usually just use the auto because if I don't have good enough patterns to do the auto, the manual, I probably shouldn't be recalibrating. So the auto doesn't work. The manual is one of those things where it can be tricky to find enough good data points to really get a good calibration off of that. And then again, the other thing is always just to double check the phase list and when you're doing a recalibration. Now, the other reason to double check the phase list is because if I'm working on a data set, I can also essentially, I can miss a phase. So I originally collected my data set, in some small area, there was data that I didn't index, it didn't index well. Start poking around to figure out the different phase. That happens all the time, especially if we're dealing with geological stuff. So, oh, I missed a phase, let's go ahead and back and re-add it. So inside of OIM analysis, I'm now able to add and remove phases. I can keep the phases in there and say just, hey, don't re-index this phase, don't use this for re-indexing. Again, it's just an easy way of doing that. The other thing to keep in mind is that the initial phase list is already loaded with the scan. Again, that's saved with the OSC file, so if I open up the OSC file, say, hey, these phases are already there. But again, I can add or remove those phases now if I needed to. So again, I'm kind of working my way through my normal EBSD steps, right? I have a background here, I have my phases listed, and there's all these things that kind of the same workflow, just in a different way of doing it because now I'm doing it after the data has already been collected. So now I have it. I have my lovely my phases listed, and I got my background, and I've done all these other steps. Now I have to actually run the reindexing, and the way to run the reindexing is just to push the button. So again, my background's been done. I've recalibrated. My phases are selected. My options are going to be now to basically just reindex a single point. So if you wanted to, and you had, I don't know, interns or undergraduates or whatever, you could say, okay, reindex it by hand, point by point. Usually not a good method of doing it, mainly because we don't have that much time. The other way is to be able to reindex the entire data set of the partition. So I'm working on a data set, the second button there will rerun the entire partition or the data set itself. The button after that has multiple ones. Is going to be the batch scan. So that runs the entire batch of scans. So you click on the button, further pops up group under settings, and you run through it doing a full run of scans. Again, this is one of those things that's highly useful if you're doing 3D work. I have 50 EBSD scans. I missed a phase. I go ahead and click this button. Underneath that is what we call the PCA. It's basically our chi-scan. It stands for phase cluster analysis or principal component analysis, depends on which language you want to use. And essentially just uses chemistry. So it has a different pop-up box, and again, it uses chemistry to help us do the indexing. I'm not going to cover this in this guide, but it's relatively straightforward to use. You basically pull up the chemistry, and then basically dragging the chemistry, the phases it finds to the phases you have listed, and then it just reindexes those phases using the chemistry as kind of an initial sort. So again, just push the button and it runs. When you push that button, it's going to pop up the next window. And this next window is basically your reindexing window. And it looks much similar to everything you've kind of seen before. Again, we have our information there on the left. But a couple things to point out here is going to be the progress bar. So between the map itself and the reindexing tab on the right side, the progress bar does two things. One, it shows how far the scan is along. So it starts at the top and works its way down. And the other thing is the color of it is telling us a lot about the CI of the data set. So I look at that and I see it's green. That means it's greater than 0.2. Yellow is usually between 0.1 and 0.2, and red basically means less than 0.1. So this is just a way of telling us, basically how well our data is reindexing. So maybe if it starts off bad, I'll just push the red button, the stop sign on the bottom there, and say, okay, I need to do something else to get better indexing results. On the left, again, you can see the map progress. The pixelation of that is just an artifact of basically squeezing the data down. Because of that, but the actual map turns out looking fine. So just one of those things to keep in mind. The other thing is that it has a status window down here in the bottom right that I can toggle between basically watching the patterns live. This shows me the background corrected patterns live. I can also watch the crystal orientations or the one I tend to use is going to be the statistics window itself. The statistic window is a little bit different than the other windows because it has essentially more data. Here you can see a little bit further along in the scan. I have more, the progress bar has gone down further. And here I can see if I click on the display stats, I can see the time remaining, how fast it's reindexing, the points remaining, and the row average CI. So the row average CI is a rolling average, basically telling me, okay, over the last X amount of data points, what was my average CI? These, again, is basically just telling me my indexing results and how much longer I have. So it's just one of those ways of checking, saying, okay, what's going on? Now, with that, after this reindexing, the next real question is, what kind of effects does this have on my data? And that's one of those questions that is, again, it's something we cover a lot in our M&M talks this year. And after those are given out, we'll probably have copies or something like that that we can share with you guys. The big things with redoing this data is that in the end, it doesn't really have that big of an effect on things that you think it would. So here's just an original data set, and here is the original versus NPAR. Again, you can just see in this case with a nickel sample, you get way better results. So this is that sample data set we showed. You can see, you can see the twins. You can see a lot of smaller features now, like this guy over around here around 8 o'clock. You can see the two twins in here, and you can start to see some smaller, finer features. And those finer features are the things you tend to actually lose, and I'll kind of show you that in a second. So in the end, NPAR does a really good job of turning noisy data sets into really, really good data sets that are consistent data that you can be happy to show. Here's the detail that's maintained. So here's actually a staple. We did it. Everybody has a staple laying around. So we use a relatively fine step size of 70 nanometers on a tungsten scope. Low beam current at high KV. You can see that on the left here, it's the IQ map before NPAR. On the right is after NPAR. You can see the grain boundaries are still there. You can still see finer details. You're not really losing anything with NPAR, except sometimes you start to lose smaller twin features. And that's really kind of the only thing that you'll seem to lose. So here is another example of maintaining that detail. Here's the IPF map for that staple. You can see here that you can see in the non-NPAR stuff, there's a lot of grain boundaries, a lot of smaller areas that are having trouble indexing, and after NPAR, those are gone. And again, the question about losing detail, here you can see that you're not losing that detail. So here you can see in some areas, you can see those small strain gradients, the small changes in colors. Those exist both in the before NPAR and the after NPAR. And again, our M&M presentations are going to actually cover this as a pixel by pixel change, and you can start to see again that these aren't. The main difference with NPAR, the things I have seen us lose, is going to be, again, small scale features. So that loss of detail happens to do with usually like small twin boundaries. So you can see here, without NPAR, you can see in the bottom left here, there's a small twin right between the two purplish bluish guys. That tends to be lost in NPAR. That's just because if it's on the size of a pixel, it gets averaged out. But on things that aren't that size, they're still not going to happen. So it's usually just going to be a small twin laminae that get removed. But again, this is just an issue of honestly your step size for your feature size was probably wrong. So in this case, you probably want to make a little bit finer step size, and that would still be there. So with that, I'm going to put up another poll and kind of get some feedback from you guys. So here at EDAX, we really want to make sure that we're answering the questions you guys want to know. So here is a poll about future topics for EBSD webinars. We have 1,000 ideas in our minds pretty much all the time, but what we want to do and what you guys might want to see could be different things. So here we just have some options up here, more on sample prep, maybe a little bit more of understanding our indexing routines, or interaction of the microscope settings with EBSD, which is something we cover relatively in depth with training courses. More like this, where it's OIM Analysis Tutorials to start pulling apart the data, understand it more. or the more practical applications of EBSD, saying, okay, here's what I'm really doing with this on a day-to-day basis. What can OIM analysis, or what can the EBSD do to help me get the information I need? And with this poll, now I'm basically going to open up the floor to questions. So feel free to ask any questions about OIM Analysis 8, NPAR in OIM Analysis, or anything else. So go ahead and let the questions fly. So the first question I currently see is a question about dynamic background corrections, and specifically with a polymer composite. I'm not entirely sure what you mean by polymer in this case. With plastics, plastics and EBSD usually don't mix because they don't diffract very well and they tend not to be all that crystalline. And because of those, you don't tend to get that great of indexing out of it. I have what's called a crystalline polymer sample on my desk, but it's just one of those things that it is not easy to do. If you mean something different by polymer, please let me know. But in general, plastics aren't really EBSDable. So while I wait for the questions to come in, which actually are relatively small right now, the webinar up here is going to. You guys are looking at, okay, well, people want to understand our indexing routine. Okay, it's good to know. And also interactions with the microscope settings and the OIM tutorials. It's good to know. See about see what you guys want. More on sample prep. Again, we just did a relatively good one on sample prep, so maybe a lot of you guys just saw that, but we can do other things about it. Got a question talking about pre-treatment of the sample. In this case, there's no special pre-treatment of the sample needed. It is just a question of, it is what it is. We always tell you that you should try to start your sample with the best sample prep you can do. So if I'm dealing with a sample, we usually say, hey, you should be using a vibratory polisher on most of your samples to get the highest quality patterns. Because I have the highest quality patterns, then I can get, basically better data. I can collect better data, I can get better results, and in the end, I can get my goal. So we don't need any kind of special sort of pre-treatment for this, but again, it's usually NPAR is best with those samples where it doesn't matter what you do, it's just not going to be the perfect EBSD sample. Again, things like ceramics, they can be very, very hard. They can be very, very multi-phase, where there's just things that diffract different. Maybe if I have a zirconium in there or something. So these basically non-ideal samples are much easier to deal with because of that. It could be polishing, it could be diffraction strength, it could be 1,000 things. Where it's just I can't get everything perfect, and that's really is where NPAR shines. And then a question about NPAR before or after cleanup. Now, essentially, NPAR should always be done before cleanup, and the reason is because I am changing my reindexing. Cleanup routines and NPAR are fundamentally different, and the fundamental difference is that the cleanup routines use the data after it's indexed, while NPAR is reindexing it. So NPAR is a reprocessing of the actual patterns themselves, while again the cleanup routines tend to be more like image processing routines. So NPAR should be done before any cleanups are done. Those cleanups should be again done after NPAR. Our standard routine is usually going to be things like a grain standard CIS, and then things like partitioning. Now, what I could do in that is I can start to pull that data apart and looking at cleanups to understand what's not being indexed well, and then go back and reindex that. So again, I can go back and say, okay, I can do these cleanup routines, but then I can basically start over after I have an understanding of my sample better to better do that. So again, anytime I'm doing a cleanup routine, it should be after the cleanup should be after doing NPAR, because NPAR is reindexing it, and cleanup should be done on indexed points. So I don't want to change the indexing on the stuff I've already done. So if you have any more questions, now would be a time to put them in. With that in mind, again, the other thing is of course, we are going to be at M&M as always. We have quite a few good talks, both in our booth and in the general presentations. So we'll have a good talk by my boss Tara, talking about 3D EDX data in a FIB. We're going to have a lunch and learn. We're able to this year bring pretty much all the brains for EBSD we have here, and we're going to talk about making the most out of your data. That's going to be presented by Renee, Matt, me, and Stu. There's over 60 years of EBSD experience with these four gentlemen, with most of it not being me, because those guys are all way more experienced than I am. We're also going to have the Ask the Expert sessions. So we've been doing these relatively routinely now as part of the Ask groups every other month. We switch back and forth between EBSD and EDS, where we're going to be basically there to answer your questions. High, low end, high end, whatever, doesn't matter. Just come there, ask us questions. And then we're going to also be doing a little bit more on EDS in life sciences. And then of course we have our final presentations, one on correlating data sets, and then the scientific analysis of NPAR that Pat is doing. So again, Pat's going to be looking at the scientific analysis of NPAR. Next question here is going to be, is it possible to average the Kikuchi patterns over more than just the nearest neighbors? Basically, can I set it as a kernel size as like the CAM maps? As of right now, we have not added that. Technologically wise, it'd be a relatively trivial thing. I think the reason we have not done it so far is because it's we're not sure if it's worth it. If your data set is such that I would need, let me go ahead and change my slide deck to way earlier. So the question is how many points would that actually be averaging? So if I zoomed out and started to take a map at, so let's go ahead and take a data point. If I started to zoom that out, I would start to lose a lot of detail across that area. So in this case, it would be closer to probably 20 data points. I'm not going to do the math right now, but it'd be more data points. You would have more loss of detail probably, and in the end, you'd probably also have more overlapping patterns. I have a feeling your data quality would probably go down if I start to do second or third or even fourth away from my center point. So I just don't think that would be a good thing. Again, there's no reason for us not to be able to do it, but I don't think the data quality would really kind of be worth it to look into it. So with that in mind, I've honestly answered all the questions. If there's any other questions, again, feel free to shoot them in now. And of course, the other thing is always, most of you guys here, and I got the list. I can see most of you guys are already in contact with me. So shoot me emails, ask me questions. I'm always happy to ask. Again, there's always plenty of these webinars. If you missed something today, you can always go back and watch it. The other thing is of course, our blogs are up there. I'm working on a series of blog posts, kind of the basics of EBSD. I'm going to try to do those relatively regularly to keep that going. And of course, these webinars are always available at any time to watch. I like to tell people, if you got that Friday afternoon where you have that 2 or 3 hour block and you don't really want to do, real work, so to speak, go ahead and watch our webinars. Do that continuing education, understand techniques better, understand workflow better. In the end, just make yourself a better microanalyst by understanding things. So with that in mind, I think I'm going to go ahead and end the webinar. Thanks for joining us. Been good dealing with you guys.